thanks to the organizer for organizing this amazing conference and also inviting me to give a talk. So I'm going to talk about the work with my student Sanjay Raman on the geometry of marked moduli spaces. So this is a conference on geometry and strings, and I think hopefully this will be a topic related to my talk. So let me remind you of the context of distance conjecture, distance or duality conjecture, with the Oguri. And the statement there was that if you consider the space of moduli, massless fields for a quantum gravity theory, at infinite distance in field space, you get a tower of massless particles whose mass go exponentially down with distance. If delta phi is the distance, if you go far into the boundaries, towards the boundary of the moduli space, you get a tower of light states with some exponents which one can actually quantify depending on whether you get extra dimensions opening up or you get a string tower. So this is all good. In that same paper, we had a few more conjectures about moduli space. I'm going to talk about some of those. So this is studied very much. And then there's this other conjecture we made, was that the curvature of moduli space, scalar curvature of moduli space, goes to a negative value asymptotically. The motivation for this conjecture was that we noticed that in all these examples in string theory, you get these kind of homogeneous spaces, at least with enough supersymmetry, where curvature is negative, so that was easy. But then there were other examples like with 8 supercharges in Calabi-Yau where the curvature is not always positive. And the simplest example was the conifold case. It's a quintic case. And in that case, if you study the moduli space, let's say in the mirror quintic, you find that in the one-parameter complex moduli, there are regions where the curvature actually goes to positive value. For example, near the conifold, it blows up. So you find the curvature which looks roughly like this. So this is the parameter, when you get to near the conifold point, the curvature blows up. So this is the curvature axis. But asymptotically, it goes to negative value. So we observed this, and so we noticed that near the places where you have matter fields in the conifold context, you have a positive curvature. So we said that if you're away from these points far enough, you always get negative. In other words, the positivity of the curvature was somehow ascribed to this conifold behavior. This led us to make this conjecture. But this conjecture actually is not quite the right way of saying it, and it's not correct. So let me explain why it's not correct, the way it's stated. We want to say we want to be away from these points. This does not mean we should go asymptotically at infinity in this variable, in moduli space, because you could have, for example, the hypermultiplet moduli, and you can move in that direction to infinity without moving at all here. You can stay right next to this guy and just go asymptotically in some other direction, and then it will not be true. So what we really should have said was that away from these points, far enough away from these points, if you can go away from these points, then you will get curvature being negative. So that would be the correct way of stating what we wanted to say. This way of saying it actually was a way which has been recently emphasized by Marchesano et al. In the context of a counterexample to the original version of this conjecture, which Tenner and Wilson brought up. In their example also, you are near a particular point in place where you have a conformal fixed point or massless modes, but then you go in another direction, which doesn't affect that fact. Very similar to the example I just told you here. So the only counterexamples to this statement would be the cases where you are actually staying near the corresponding point. So somehow, if you go away from the points where you get quantum field theory, the curvature is negative. So that's the moral of that. But I will come back to this. I want to rephrase this still. So that's one of my aim points, one of my main points in this talk, to give you a different version of this same conjecture, which actually does not require you to talk about going away from these points. One other conjecture we had with Hiroshi was that the pi1 of moduli space, suitably defined, and I will mention in a second what I mean, is trivial. Now, what do I mean by pi1 of moduli space? It's not the usual pi1. What we meant was that if you take a geodesic in a particular class in the moduli space, there is no minimal length geodesic in that class. That means if you choose a class, then you can shrink it further and further to be arbitrarily small. In that sense, we said that there is no element which represents the minimal cycle. That's what we meant by here. There are no counterexamples known to this. So this is presumably correct, or it could be correct. But we did not make any conjectures about pi n. In fact, these are not trivial. For example, a simple example of it is the moduli space of a torus, or type 2b as a function of the coupling constant. The moduli space is the usual upper half plane modulat by SL2Z, and this gives you something like S2, and then if you consider wrapping the second homology around S2, or second homotopy is Z, and it's not 0. And so therefore this is the not trivial. Okay. Now I want to connect this to cobordism conjecture. You see, cobordism conjecture is kind of like saying everything can be gotten rid of, including pi n of anything, if you go onto the field space generally enough. Here, however, we are restricting ourselves to massless fields. So for massless fields, it doesn't have to be 0. So the way, for example, cobordism conjecture works in this context is that if you took a class and wrapped around this fundamental domain of this moduli space, like S2, like if you wrapped it 24 times, you would get K3. If you wrapped S2 24 times around this moduli space, you get the elliptic vibration over K3, over P1, which gives you K3. So that one can be undone by going away from, presumably, nobody has constructed it, but it will go away from a minimal massless sector in order to be unwound. That's what we believe. You should break supersymmetry, and therefore you will not be able to undo this by not going away from the vacuum sector. So therefore, there's no contradiction with cobordism conjecture for this not to be trivial, because we are restricting our attention only to the vacuum sector. Now, in this talk, I'm going to restrict my attention to the vacuum sector, but I want to somehow get some things which all vanish. I want somehow to replace this by a vanishing condition. Sounds like a contradiction, because how could you? This is the counterexample. So this brings us to the next point. We got this is the instructive example. How did we get the upper half plane modulat by SL2Z? Is first of all to start with the full upper half plane. But upper half plane is naively not the physical space, because there's, by SL2Z symmetries, there's a gauge symmetry, so therefore the physical space is actually smaller, is just by this symmetry. However, if we define the notion of what we call the marked moduli space, which I will define now, the marked moduli space is the space of the vacuum of the theory together with basis of observables. So for example, in the case of type 2b, the vacuum is parameterized in 10 dimensions by tau, but there are physical observables like D branes or NS branes, so you have PQ strings and all that. So if you look at that labeling of the physical states, if you go, for example, from tau to -1 over tau, you get the NS strings being exchanged with D strings, fundamental strings exchanged with the D strings, and therefore tau goes to -1 over tau is not a symmetry of the marked one, because you have picked observables. So with the observables, the symmetry that you had would be gone. So the physical space, together with the observables, will actually be the covering of the fundamental of the domain, and which gives you the upper half plane. So this gives you what we usually call the Teichmüller space. Okay, is that clear? So we have a motivation for defining a Teichmüller space in a physical way. The reason for terminology of mark is that, for example, when mathematicians talk about Riemann surfaces and marked Riemann surfaces, they choose a basis for one cycles, and that's a marking on the Riemann surface. So this is in that sense we are using this terminology. Marked in this case means take into account observables. So the first conjecture we are making now is that this space is contractible. In particular, this means that pi n of it is 0. The marked moduli space I denote by m hat. This sounds a little more like cobordism conjecture. Of course, now this is the vacuum sector. So that's the first one. Now, the second one is that has to do with the following. Is to step back and see how do you prove contractibility of a space. Well, it's not necessarily trivial to prove a space is contractible, but one technique that's very often used in math to prove contractibility is to have a metric on the space and draw some kind of geodesics in this space, and if the geodesics are unique, to use that to contract the space. Is that clear? In other words, if you have a unique geodesic between every 2 points, then you can use that to retract it to a point, each one. If you start from a given point to any other point, being unique means you can contract it. So for some reason, we had unique geodesics between pairs of points. This would have been like this. So in fact, there's a theorem, when do you get to such a situation is captured by a theorem by Cartan and Hadamard, which says that if the pi 1 of a space is trivial, and the sectional curvature is negative or less than or equal to 0, including negative, it's not, in other words, it's not positive, then the space is contractible, and between each pairs of points, there's a unique geodesic. Well, this is not surprising, perhaps, because if you have sectional curvature being negative, which means if you start with a given geodesic, the nearby geodesics will diverge from each other by the curvature term. It's negative, and so therefore they won't intersect. And therefore you can use that to retract the space. If there's a fundamental group is non-trivial, you could go 2 different ways and get there, so that's the only way you can violate it, but we're assuming that there's no pi 1, and so that's basically the rough argument of how you prove it. So how do you prove the marked moduli space is contractible? Would be this kind of idea. If you have a metric which has negative curvature, negative sectional curvature, this would imply unique geodesics, and this would imply contractibility. What do we want? We want to somehow get to the point where the m hat being contractible. But we know this is false. We know there are regions for which R is positive, so this is not true. But if this is still true, you're fine. So we want to actually propose the second conjecture, which is the second statement here. which is quite a daring statement, as I'll try to explain. So the second conjecture is, sorry? Oh. So the second conjecture is that between any P and Q in the marked moduli space, there's a unique geodesic. Now, geodesic with respect to what? With respect to the physical metric. Physical metric can be read, of course, from the kinetic term for the massless fields, as usual. So the statement would be that this will be still true. Now, this is super risky. Just look at the conifold case. Curvature is positive in some regions. So therefore, the geodesics wants to go the other way. And so therefore, is this really true? So we started posing this question, like, could it be contractible because this is still true? Now, one could be a little bit less daring and say, well, maybe this is true asymptotically or far away from these bad points, the conformal field theory points, in which case it's probably a good bet that's true. But could we actually have a stronger statement? Because if this stronger statement is true, it will imply the first conjecture. So the second conjecture, that between any pairs of points in marked moduli space, there's a unique geodesic, basically does what we really want to say about contractibility. Before talking about the dangerous cases, let's talk about easy cases. Let's consider theories with the number of supersymmetries bigger than 8. In these cases, the moduli space is more under control, and indeed it's negatively curved. For example, let's just take the case with n equal to 16 supercharges that you're all familiar with. You get things like Narayan moduli, SOP comma Q, over SOP times SOQ. So this, without quotienting by the usual duality group, this space is contractible and it is negatively curved. So this is a simple example where this is true. And the similar cases for higher than 8 supercharges. So these are easy cases. So it's kind of like, okay, what about the more interesting cases? Well, the n equals to 8 case, 8 supercharges, which is the case with n equal to 2 supersymmetric theories and d equals to 4, or n equals to 1 and d equals to 5, these examples are the next kind of classes that you might ask. As I have explained here, the n equals to 8 is not going to have only positive curvature. We have also negative curvature. It can have positive curvature. But the first theorem is that the marked moduli space at least for the vector multiplet part, is contractible. This is a math theorem. This is known. Yes? Yes?
So it's true that that space is a homogeneous space. It's perfectly smooth. Every point looks like every other point. But physically, we know there are loci where, for instance, in the Narayan moduli space, we get non-revealing gauge symmetries, and there are singularities of the vacuum
Yes.
theory, right? Because they're extra massive states.
Yes.
That's totally invisible when I go
Yes.
to
Yes, it is. You're right. It is.
So is that a physical thing to do? Because those points now look totally smooth points.
Well, I mean, you're right that there will be interesting physics going on, and you may want to have some other gauges of physics there. That's certainly a good thing to look for, but it doesn't prevent one from studying the masses moduli still.
No, but the physical metric in the Moduli blows up there, right? Because they're extra massive.
No. The physical, no. In this case,
The homogeneous metric on this space is perfectly smooth there.
this is the physical metric, does not get corrections. That's the point. For n equals to bigger than 8, they cancel between boson and fermions. So that's your intuition is based on this case, which I come to. For this case, you're correct. For the lower supersymmetric case, you're correct. And this curvature blows up. We'll come to that. For the higher supersymmetric case, they just cancel. Even though, for example, take the K3 case, ADE singularities. You won't get a singularity on the metric. You'll get a moduli space, which if you quotient out by ZN symmetries and so on, you'll get the orbifold symmetry. But on Teichmuller space, you won't see any of that. It's nothing going on strange in that case. Even though there is ADE singularity, you get gauge symmetries and all that. So there's nothing bizarre here. This is very much like the SF upper half plane we just discussed. Tau equals to IK.
Orbifold singularities. I realize that the metric away from the orbifold singularity is perfectly smooth.
No. Let me talk about the very specific case so that you're with it. I'm talking about that too. Let's take T2 case. You have the upper half plane times the upper half plane for tau and rho if you take the complex and Keller structure. Just like what you say, at some particular points you have SU2 times SU2 and all that stuff. Yeah. But the metric is still the upper half plane metric exactly, not corrected. That's the Norai metric. So it does not reflect that aspect, but in the lower supersymmetric case you will see it. So your question is valid for the next case, which I will come to. Anyhow, so in this case, there is no problem. In the other case, when you have less supersymmetry, like n equals to 8, there's actually a mathematics theorem that I will explain in a second, that the Teichmuller space, which is the analog of what I'm calling as the Mark moduli space for vector multiplets, is contractible. How do the mathematicians prove it? The way they prove it is that they actually have a metric on this space which has negative sectional curvature. Sectional curvatures are all negative or 0. Okay. Which metric is that? It is not the physical metric. It is not what they would have called the Weil-Petersen metric. It's the Hodge metric. So there is some metric you can define on that space, on the Mark moduli space, which is related to the physical metric by some formulas. Like there's a Kähler metric on it, which is given by the physical metric up to some factor like the number of vector multiplets plus 3, plus the curvature metric. So if you add these up, gives you another metric, natural metric. For this one, you can show it is negatively curved. Using that, you can show, therefore, there's unique geodesic with respect to that metric, and it's contractible, which is what we wanted to have. But, albeit this is not the physical metric. So therefore, it's a bit strange to study geodesics like the mathematicians would do in this space, with using the metric which is not what we call the physical metric, even though this metric is natural. So the way the Hodge metric is defined is by using the period embedding, and you can embed the moduli space into the space which is SO2n plus 2 divided by SO2n times, SP2n divided by U1 times UN. So by mapping the space into the symplectic group, you can use the properties of this and pull back the metric, and that's what's called the Hodge metric. And using that, you can show this contractibility. So we already know that the first conjecture, at least for the vector multiplets for n equals to 8, is correct. So the question is whether the second conjecture is also correct or not. In other words, can this property be also true for the geodesics with respect to the physical metric? Well, Obviously, the most dangerous points are near the regions where the curvature blows up, for example, near the conifold. So indeed, the conifold case was studied by Blumenhagen et al. In the context of the quintic mirror. So they studied the conifold has these interesting points, Landau-Ginzburg point, the psi equals to 1, which is the conifold point, and the infinity direction. So they studied the geodesics in this space. It's not quite trivial. Even though the metric is exactly known, it's not a trivial thing to actually solve it, so they did it numerically. So what they found was that if you look at geodesics near this region, which starts from the Landau-Ginzburg point, when you go towards it, you're fine, you can go directly to the conifold. If you go a little bit away from it, you come back down, and then if you go this way, you come back down, but then they cross right there. So they seem to cross, and that would give you a contradiction. We first thought this was contradiction, but it was not. And the reason is, you're going around the conifold point. Conifold point is not the same point on the moduli space. You're on the marked moduli space, you're undergoing tau goes to tau plus 1. So you're going on a different sheet. So they intersect on the moduli space, but not on the marked moduli space. So then you say, okay, can you actually understand what is going on? So we studied the near direction to the near region for the marked moduli space near the conifold analytically, and we proved they will not intersect. They will always go around it, despite the fact that it had a chance. Then we went to another series of examples given by Tenner and Wilson. This was the other counterexample that involved the positive curvature case, and this corresponds to 4 cycles shrinking inside the Calabi-Yau. So you have a 4 cycles shrinking inside the Calabi-Yau, and if you have these directions of the Kähler parameters, let's say Z1 and Z2, some directions, if you go into 2 different directions, there are 2 different ways you can get. In each cases that you do, again, you prove analytically they don't intersect near this region. So the geodesics come close, but they don't intersect. So we then went to other examples, like Argyris-Douglas. Argyris-Douglas, again, you have singularity, like what Jacques was saying. So in that case, if you write the metric for the, let's say, the simplest Argyris-Douglas corresponding to the curve of y squared is x cubed, indeed, at the origin, you get a singular curvature, like conical singularity. And of course, if you do the conical singularity one, if you go around it, you would of course intersect. But again, as you go around it, the only way to intersect is going around the Argyris-Douglas point, in which case you pick up monodromy and some physical state undergoes change. And therefore, on the marked modular space, again, they don't intersect. So I think I'm beginning to run out of time, so let me basically make the summary of a point. So we are making a daring conjecture, which has all the chances of being false by choosing the example, because there's a theorem that all the 4D n equal to 2 quantum field theories have positive curvature. So therefore, there's a huge plethora of examples that one can try to find these geodesics in the corresponding marked moduli space and see if they intersect. Studying them is not totally trivial, unfortunately, otherwise we would have done it. But it would certainly be an interesting thing to study. And if they indeed don't intersect, to try to come up with an argument why they wouldn't. Now, if one finds a counterexample for that statement, then one could ask the next question whether or not the asymptotic version still works, that you do intersect or not, and basically understand the interplay of this geometry with the contractibility. I think the strongest statement, we believe, is the contractibility of this marked moduli space. And the question even for that is why? Why it should be contractible? Okay, I will stop here. Thank you.